Hey guys, what's up? Welcome back. Pretty much done with the exams. I think I have like one or two that I had to figure out what to do because they came in a bunch of different files. So still working on one or two of them, but they're done for the most part. Decent scores overall, not great, not bad, but yeah, so it's looking okay. Yeah, so exam 1's done. Headed to exam 2. We're going to be chapter 14 and chapter 15 for the most part, or at least halfway through chapter 15 on the second exam. And today we start chapter 15, which is double integrals. So double integrals over rectangles for today. So double integrals over rectangles. And eventually we'll get to double integrals over general regions after today. So let's look at let's just look at what we did back in Calc 2 first of all. So recall integral from a to b f of x dx was equal to the limit as n goes to infinity of the summation I goes from 1 to n f of xi star delta xi. So the definite integral was defined as a limit of a Riemann sum, and what we did was we took our curve f of x over the interval ab and broke it up into a bunch of rectangles to approximate the area under the curve. Maybe using left endpoints or something like that. So an integral was a limit of a Riemann sum. So it was a limit of a Riemann sum. And we basically were trying to find the area under the curve. So the integral was the area under the curve. That's what we kept saying in Calc 2 over and over and over. Integral is the area under the curve. So today what we're going to do is we're going to look at a function of two variables. So now consider z equals f of xy. Some surface in the two-dimensional, or sorry, in the three-dimensional space. Like it could be a hemisphere, paraboloid, whatever. Say something like that. Some surface. Z equals f of xy. And let's say in the xy plane, we define a rectangle. And we only want to find the area, or the volume, I should say, the volume under the surface over the rectangle. So we are essentially reducing this down to something like this. So the question is, what is the volume under f of xy, but over the rectangle in the XY plane. And we'll call that rectangle R. So we're trying to find this volume in here above this rectangle under the surface z equals f of xy. So what we're going to do is kind of do the same thing. We're going to break up our solid, our volume, into a bunch of little rectangular prisms, and then find the volume of each little rectangular prism and add those together. So we will approximate the volume using many small rectangular prisms. So that's kind of how we're going to answer the question of what is the volume under the function f of xy, so below the surface but over the rectangle R in the xy plane. So that's kind of our goal. That's how we're going to approach this. So we're basically going to have a bunch of little rectangular prisms that are somewhat approximating the volume under this surface. So let me just try to draw this again. So what we're going to do is we're going to take this rectangle in the xy plane. So we'll say x is going this way, y is going this way, z is going this way. We're going to take this rectangle and break it up into a bunch of smaller rectangles. So we're going to cut it up in the x direction, we're going to cut it in the y direction, and create a bunch of smaller rectangular prisms. We're going to add them all together. So you get the idea. So in the xy direction, we have a rectangle. Call it the rectangle R. And it goes from x from A to B, and y goes from C to D. And what we're going to do is we're going to cut the x direction into little lengths delta x. Delta x, where delta x is going to be b minus a over n, and n is going to be the number of subdivisions for x to get delta x. And then same thing for y, we're going to cut it in the y direction. And get a distance here of delta y. And delta y is going to be d minus c over m. So n is the number of subdivisions in the x direction, and m is the number of subdivisions in the y direction. Very similar to how we did Riemann sums for a function of one variable. We're doing a double sum, basically, is what this is going to turn out to be. And if this point is xi plus 1, we'll call this yj, and yj plus 1. Then this point at xi, yj defines a rectangle, and this rectangle we call the rectangle rij. So it's a certain rectangle, subrectangle. So rij is the rectangle whose lower left corner is xi yj. And now let xij, call it xi star, yj star be any point in rij. So basically just pick any point that you want from this subrectangle. I'll just draw a white dot right there to represent the point. And the area of this subrectangle is delta A. So delta A equals delta x times delta y, which is the area of the subrectangle. And then f of xi star yj star is the height, or will be the height of the rectangular prism. Above rij. So then the volume, V, is going to be approximately the double sum. I goes from 1 to n. Let me say 0 to n minus 1. From 0 to n minus 1. And j goes from 0 to m minus 1. F of xi star yj star delta A. Because this multiplication here is basically the volume, delta volume, over each prism, each small prism. And you add all the volumes of all the little prisms together to approximate the volume under the surface above this rectangle. So that is the double sum that is approximating the volume that we want to find. And then take the limit as m and n go to infinity, and that's the definition of a double integral. So definition. The double integral of f of xy over the rectangle R over the rectangle R is double integral symbol, so two integral signs, over the rectangle R, f of xy dA equals the limit as m and n both go to infinity, summation I equals 0 to n minus 1, summation j equals 0 to m minus 1, f of xi star yj star delta A. If the limit exists. So if the limit exists. So that's what we mean by a double integral. It's the limit of this double sum, basically a bunch of rectangular prism volumes added together. What's the limiting volume that you get? Then that is the volume under the surface. So today we're going to stick to the discrete approach of breaking it up into a bunch of rectangular prisms and using different points inside of each little subrectangle Rij, and then approximating the volume using number crunching. Next time we'll get into how to actually do these double integrals, like as an iterated integral. But for today, just doing the approximations with the Riemann sums and keeping it discrete. So note, we have many options for a point in the rectangle Rij. If we just look at this a lot more closely, say I just make one big Rij here in the middle. Well, then there are a bunch of different points that we could pick. We could pick the lower left corner. We could pick the lower right corner. We could pick the upper left corner. We could pick the upper right corner. We could pick the midpoint. We could pick any point we want to inside of this little rectangle Rij. So it just depends on, your preference, I guess. So this red point is the lower left corner. This orange point is the lower right corner. The upper left corner, that green color, upper left corner. This blue point is the upper right corner. And then the mint is the midpoint of that rectangle. So the midpoint of the subrectangle. So there are many options. These are just 5 commonly chosen points. So you might say, okay, over every rectangle, I want to use the lower left corner. And that would be a lower left corner approximation. Kind of like we used left endpoints and right endpoints and midpoints for Riemann sum approximations. This is like a similar concept. So similar to using left or right endpoints for single integrals. So we're going to stick to these 5 points for this class. I mean, doing the rest is okay. It's just not common. Of course, by hand, this is all silly. This is just to get the conceptual understanding. You would do all of this on a computer if you needed to like numerically approximate a double integral. You wouldn't be doing this by hand in practice, of course. But this is just to get the concept down to really understand what we're doing before we move into symbolic integration. So let's look at an example here. I see there's a lag today, and I'm not sure why there's a lag. I don't have anything running in the background today, so not sure. But let's look at an example. Approximate the volume. So approximate the volume beneath z equals x squared sine of pi y over 6. So beneath that surface and above the rectangle R equals the set of ordered pairs x, y such that x is between 0 and 6, y is between 0 and 6. It's actually a square. So above this rectangle, using upper right grid points and 4 subrectangles. Z equals so beneath that circle R equals y such that x is between 0 and 6, y is between 0 and 6. Okay, not sure what's up with the lag. Pretty bad lag today, so just try to hang in there with me. Sorry about that. Let's see, solution. I'm going to draw this rectangle because that's the most important part. It doesn't really matter what the surface looks like, to be honest. So this rectangle is from 0 to 6 in the x direction, 0 to 6 in the y direction. So here is our rectangle. It's actually a square. And if we want to divide this rectangle into 4 subrectangles, all I have to do is cut this in half right here at 3, x equals 3, and then cut it in half right here at y equals 3 as well. So that creates 4 equal sub-rectangles. And then it tells me to use upper right grid points. So for the first rectangle, I'll call it just R1, even though I should call it R00. This is going to be my upper right grid point for R1. So R1, we use the point 3, 3. For R2, we use the point 6, 3. For R3, we use the point 3, 6. And for rectangle 4, we use the point 6, 6. So these are our upper right grid points. So these are the upper right grid points. Just gonna check something really fast. Okay, maybe that'll help. Okay. All right, so we got our upper right grid points, and now the volume is going to be approximately delta A times f of 3, 3 plus delta A times f of 6, 3 plus delta A times f of 3, 6 plus delta A times f of 6, 6. So it's like the volume over each little rectangle gets added together. So this is delta, we'll call it delta V1, delta V1, delta V2, delta V3, and then delta V4. It's like the volume over each little rectangle. And we're adding all of those together. So what is the delta A? Well, delta X is 3. We can see that here. Delta X equals 3. And same for delta Y. Delta Y is 3. So delta A is going to be delta X times delta Y, which is 3 times 3, which is 9. And I can actually factor that out completely from what we've got. I can just say 9 times, and then plug this 3, 3 into our function. So here's our function, x squared sine of pi y over 6. So 3 squared sine of 3 pi over 6 plus 6 squared sine 3 pi over 6 plus 3 squared sine 6 pi over 6 plus 6 squared sine 6 pi over 6. And what do we get? Well, these are going to be 0. So this is 0. This is 0. This is going to be a 1. This is going to be a 1. So this is going to equal 9 times 9 plus 36. And that ends up being 405. Yeah, 405 units cubed if it's volume. So assuming volume is what this represents. But yeah, approximately 405 units cubed. Okay, sorry about that. Trying to figure out this lag. It looks like we may have figured it out. So let's see if that's any better. Sorry about the lag. I feel like it's getting better. All right, so that was an approximation using 4 subrectangles and then upper right grid points. Well, how can we get a better approximation? What did we do to get better and better approximations? Well, we could either make the rectangle smaller, or we could use different points. So let's use different points instead. So example, do the same problem but use midpoints instead. So example, same problem but use the midpoints instead. All right, so solution, draw the same setup, but this time we're going to use midpoints. So from 0 to 6, in the x and y directions, and 4 subrectangles still. So again, this is 3 and this is 3. This is 0. And if we're going to use midpoints, then we're going to pick this point right here, this point right here, this point, and this point for R1, R2, R3, R4. So what are these midpoints? Well, for the first rectangle, the midpoint is going to be 1.5, comma 1.5. All right, it's halfway between 0 and 3 in each direction. So this is like 1.5. Same here, 1.5. Up here is 4.5. Over here is 4.5. So for R2, our midpoint is going to be 4.5, comma 1.5. For R3, we're going to see 1.5, comma 4.5. And for R4, we're going to use 4.5, comma 4.5. And those are our midpoints for each subrectangle. Delta A is the same, right? Delta A is still 3 times 3, which is 9. That has not changed. We did not change the size of the subrectangles, i.e. we didn't change how many there were. So all we're going to do now is add up to get the volume. So the volume is going to be approximately delta A times f of 1.5 comma 1.5 plus dot 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 delta A times f of 4.5 comma 4.5. And I should probably use the fraction equivalents of all these, but that'll be 9 times, let's see, 3/2 squared times sine of 3 pi over 12 plus dot 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 plus 9/2 squared sine of 9 pi over 12. And if you crunch that out, that's approximately 286. Well, let me give you the exact answer from this. It's 405 times square root of 2 over 2, which is approximately 286.38 units cubed. That's quite a bit different from our upper right grid points. It seems like our upper right grid point's much larger than this value. And I can go ahead and tell you the actual value of the double integral, and we'll figure out how to do that next time. But the actual value is v, which is 864 over pi, which is approximately 275.02 units cubed. So the midpoint approximation is much, much better, at least for this double integral. So midpoint is much closer. Midpoints here are giving a better approximation. So for this problem, midpoints give a much better approximation. So the evaluation point makes a big difference. Picking a good evaluation point makes a big difference, but also changing the grid size will also make a difference. So another change we can make is to the grid size. So that just means make delta x and delta y smaller. Which really just means use more subrectangles. So let's do the same problem, except use 9 subrectangles. So example, same problem. With 9 subrectangles using, first of all, upper right grid points, and then second of all, using midpoints. So let's draw the same diagram for the same rectangle in the XY direction. But now we've got to create 9 rectangles. So if we're going to do that, I'm going to cut this one into thirds. Let's see, that's not a very good cut. Cut into thirds in the X direction, cut it into thirds in the Y direction. And that means these 2 points here are 2 and 4. And same thing here, 2 and 4. So we can see here delta X is 2, delta Y is also 2. And now we have 9 rectangles. And first of all, upper right grid points on each rectangle. So we're using 2, 2, 4, 2, 6, 2, etc., all the way up to 6, 2, or sorry, 2, 6, 4, 6, and 6, 6. So that would be our midpoint approximation. Those are the points, or sorry, the upper right grid point approximation. So the volume would be approximately, let's see, what's delta A? Delta A is going to be 2 times 2, which is 4. So it'd be 4 times f of 2, 2, plus f of 4, 2, plus dot, 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 f of 4, 6, plus f of 6, 6. And we have to crunch all that out, but we get something around 306 or 325.6256 units cubed. So it's better than the 4 rectangle upper right grid points, but it's still not as good as midpoints with 4. So let's see what happens if we use midpoints with 9 rectangles. So we're going to get these midpoints, and our midpoints are the points, well, this is going to be 1, 3, 5. So 1, 1. It's going to be our first midpoint, and then 3, 1, and then 5, 1. And then at the top, eventually we're going to get to 1, 5, 3, 5, and 5, 5. And those are all of our midpoints. And then our volume is going to be approximately delta A, which is 4, times f of 1, 1, plus f of 3, 1, plus f of 5, 1, plus dot, 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 f of 5, 5. And again, we just crunch that in our function. Add them all together, we get 280 units cubed. So 280 is actually smaller than 286. We had 286 from our midpoints with 4 rectangles, 280. So we're actually getting closer to the volume that we said was 275.02. So midpoints are getting really good, especially when we get to higher numbers of subrectangles. Any questions so far? So midpoints are looking pretty good for at least for this problem. It's not always the case that midpoints give you a better approximation, but it is for this problem. So good questions there over in the chat. How do you know that delta x is 2? Because we're cutting the x-axis into thirds to create 9 subrectangles. That means that m and n are both 3 basically. So m equals 3, n equals 3, and delta x was going to be 6 minus 0 over 3, which is 2. Delta y is going to be 6 minus 0 over 3, which is 2. So that's more of an explicit computation there if you want to see that. Good question. Wow, I lost the audio again. I would say f of 3/4 comma 3/4 is about 11. So basically what we're doing is we're having to estimate the function values at these midpoints because we only have contours. And so we're kind of saying, okay, I think the function value is approximately this value here. So we're going to estimate this double integral over this rectangle 0, 1, 0, 1 by using these 4 subrectangles with midpoints. So we have to estimate the function values from the contours instead of like explicitly calculate them because we don't really have f of xy given. So here, the volume would be approximately delta A times f of 1/4 comma 1/4 plus dot 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 f of 3/4 comma 3/4, which would be 1/4 times approximately 11 plus 9.5 plus 14 plus 11. And I'll say that that is about 22, 36, 45.5 over 4. So let's see, 11.75-ish. Something like that. So I think that's 375. So that would be approximately the value of our double integral. So we could say double integral over the rectangle R f of xy dA is approximately 11.375. Not exactly, but approximately. That's an approximation. So any questions? I am terribly sorry for today. I don't know what's up. Yeah. Got most of it resolved now. Audio issues. Man, lagging issues. Sorry about that. Any questions? All right, if no questions, I'll see you guys next time. Sorry about all the difficulties today. It's on me trying to figure it out, so sorry about that. I'll try to be good to go by next week. So don't forget, no class on Monday. No class on Friday. We have the Independence Day holiday, so have a good weekend. Enjoy time. Enjoy some fun and fireworks or whatever it is. So have a good weekend. See you guys.